Hey, thank you, Sanjay. So, it's been kind of a tough week, and I see the audience is looking a little thin, for reasons I can well understand. I found as I went to prepare this lecture, this is really in the lecture notes that are posted. This is really the high points of lectures 12 through 18 in the notes. And so there's some really beautiful examples in there, but they require building up a little bit of mathematical apparatus. So, I was very inspired by Mukund's lectures this morning. So what I would urge you to do is, if this is at all interesting to you, take a look at the notes. And you may have noticed that you received an email with a PDF of the textbook we used. So, the material is all there. And so what I want to do is hit a couple of key points, okay? So I'm going to talk about hypothesis testing today. And I remember in the first or second talk, someone asked a question, and I realized when preparing, I may have misheard it a little bit. The question was, what do you have to do if you need to compare two different statistical models? Okay, and often that comes up in very complicated situations, but at a basic level, that's what I'm going to talk about today. Okay, and the situations where this comes up well, there's all kinds of situations. Okay, for example, pattern recognition. You have some kind of representation from, say, a photograph, and it has some pattern of pixels. Okay, you want to recognize letters. So, is that a K? Is it an L, an M, and so forth? Okay. This is fundamentally a statistical test. And this is a particularly simple statistical test because there are a series of very, very discrete hypotheses. It's got to be one letter or another letter or another letter. You can have other situations, for example, classic things that you find in statistics textbooks have to do with things like industrial quality control. You run some factory, you're making some component, some number of them are defective. Okay, you need to figure out whether your process is working well enough or not. And sometimes that particular case is interesting. The case of, for example, quality control is this relates to the example I gave to failure tolerance because, for example, you're counting the number of components that fails, and you have to estimate a probability of failure, okay? So in this case, you're looking at your hypothesis in connection with an estimation problem. Okay, so this problem is called hypothesis testing. And, one theme of these talks has been that every time we give up something and we get more back, okay? So first I talked about Bayesian inference, where what we came up with was a probability distribution, and we narrowed that down to point estimation. And today I'm essentially going to talk about 0-1 choices. Okay, they can be very, very complicated. So one example, so there's some great classical examples in the notes, but the background of these tests is a lot of them were developed, and in particular, one that I'm going to talk about today, you can have situations where you have multiple things going on at the same time. For example, there's a very classic case due to Francis Galton, and this certainly has to do with some evolutionary questions in a somewhat distant way. For example, is there selection when people get married based on height? And this is data for 205 couples. And he classified them as tall, medium, or short. Okay, this is the height of the wife, the height of the husband. And so there were 18 tall matches and 20 medium tall matches and 12 tall short matches. And you have similar data elsewhere. And then the question you want to ask yourself is, you want to test whether there's selection based on heights or whether the heights are independent. So essentially, the test that you're doing is you're really doing a series of tests at once. You're testing for independence. Whether the probability of a tall match is just the product of the probabilities for tall, for husband and wife. In other words, you would be having to estimate theta tall. Is it the product of theta of the husband's height and theta of the wife's height? And so forth. Okay, I just wrote the first row, but you see what you're actually testing is you're testing all of these relationships across the table independently. Okay, and that was the root in the history of statistics where one of the statistics I'm going to talk about today was developed. Okay, I'll give a variety of examples. So what I want to do is sort of hit the high points. Okay, I want to lay out the way we talk about these things in terms of false positives, false negatives, and this wonderful word power. I want to talk about the way that you compare these models. Okay, so in this case, you're distinguishing the model of independent of height. Selection for marriage is independent of height or dependent on height. Okay, so independent or other. Okay, in that case, those are the two hypotheses. And it turns out that a concept that we brought in last time, okay, the idea of likelihood, is the key to doing that. Okay, what we want to do is we want to compare the likelihoods of the two models. Okay, now, to the extent that time allows, I'm going to show you how doing that with the ratio of the likelihood leads to a very famous statistic, okay, called chi-squared. Okay, and in the lingo that statisticians use, the statistic is just some function of the variables that you use to draw conclusions about the problem that you're trying to solve. Okay, and so get ourselves oriented. Let's start with simple hypotheses. Okay, this is the really easy case. It's a case that comes up very rarely. It has some beautiful theorems associated with it. So this is often good place to start. Okay. So simple hypotheses, okay? And what I mean by simple is that the distribution is given no parameters to estimate. Okay, now, as usual, we have some data, X. And then we have the model, okay? This could be the theta hat for maximum likelihood, but we're going to have some kind of model given by X, by theta, given X. And now we want to distinguish between two models. Okay, so if the person who asked that question a couple days ago is here, I think I may have misinterpreted your question. This whole lecture is the answer to your question, at least for elementary cases. Okay, and inspired by Mukund, okay, I will say, for the details, check the books. Okay, I think there's one thing that's wrong with a lot of the sort of statistics classes that people take, and the way that a lot of the elementary textbooks are put together, okay? Because they're really collections of recipes for doing these kinds of tests. And they will say to you in the book, oh, if you have such and such a problem, use such and such a test, and then they direct you to some table in the back of the book. And this leads to this kind of rote usage of statistics, okay, which is not the way you want to think about it. Okay? Now, let me sort of lay out some of the basic notation that gets used. Okay, so hypothesis 0, that might be, say, theta equals theta 0. And that would be, or that's equivalent to saying that the distribution of X is F of X given theta 0. Okay, there'll be another hypothesis, H1. That's that theta equals theta 1. Okay, or the distribution of X is F of X theta 1. Okay, now in a lot of cases, you're asking essentially whether you're seeing an effect for some manipulation, okay? So this H0 is called the null hypothesis, okay? And the very first examples I'll be giving, they're really symmetric. You could have it either way, okay? But in a lot of cases, for example, this test for independence in the contingency table, you're sort of saying, is it independent or is it other? There is selection. You're not saying what the selection is. And in that case, the idea would be independence would be H0, the null hypothesis, and H1 would be selection. Okay? Now, how do you distinguish? Okay, well, for simple hypotheses, there's actually a very nice math result. Okay, it's the Neyman-Pearson lemma. Okay, and it's really quite old, from early in the previous century. And it says that the best test to use, okay, in a similar sense, that maximum likelihood estimator is the best estimator. Okay, and I can make that rigorous a little further. Okay, but it says that what you should do is you should compare the likelihoods. Okay, and so remember that we also wrote this as the likelihood theta. And so the idea is that you should reject H0 if f of x given theta 1 over f of x, over theta 0 is bigger than some constant k. Okay, and actually, okay, so that, in some ways, that's the essence of this whole lecture, okay? I talked about posterior distributions. I talked about likelihoods last time, okay? And so the summary then of this lecture is if you're comparing two different models, two different hypotheses, each connected with a distribution, you should compare their likelihoods. Okay, and everything else I'm going to say has to do with technical details about how to do that. Now, also last time when I talked about maximum likelihood estimation, I introduced some quality control measures. Okay, so it's very important to have quality control measures. You've got to know how well you're doing. So here's some really important ideas, or really important things to keep track of. Okay. Alpha is the probability that we reject H0 even though H0 is true. Okay, you never get something from nothing. Okay, and this has a special name that it's very important to remember, okay? This is called a type 1 error. Or a false positive. Okay, then there's beta. That's the probability that you accept H0, the null hypothesis, but H1 is true, okay? We want to accept H0 if H0 is true, and we want to accept H1 if H1 is true, okay? So this is called a type 2 error. Okay, or a false negative. Now, of course, what you're interested in is how good is your test at getting the right answer. Okay, that's sort of the practical thing you're doing. You test some piece of data, you find some cool effect, you write a paper, you get a press release. That's what at least some people like. And so you want your test to be as effective as possible, okay? So we also wanted to find pi, which is 1 minus beta, okay? That is the power of the test. Okay, that's the ability of the test to find a signal, okay? I'm saying a signal meaning H1, okay? That's like some effect, selection with husbands and wives, as opposed to no effect. That would be H0. So, yes. Oh, I'll be saying more than enough about K. So, I mean, the thing is that to define K, you need to know some things about the distributions of the likelihoods. In order to know some things about the distributions of the likelihoods, you have to start writing down likelihoods and making computations with them. So yes, I've invoked K, but the idea is we have to impose a threshold here, okay? Obviously, the bigger L of theta 1 is compared to L of theta 0, the more likely it is that H1 is true. Okay, but we're dealing with probabilities. Okay, so here I'm just saying we have to draw the line. Okay, now this is obviously a problem because we're looking at probabilities, we're looking, the data is noisy and we have stochasticity at the heart of this, and yet we want to make decisions in the face of uncertainty. Okay, so you have to draw the line somewhere, and then wherever you draw the line, you're going to have problems. Okay, so remember in the very first lecture on Bayesian statistics, I gave examples about lie detector tests and HIV infection. Okay, and there was sort of a problem because depending on the nature of the population, whether they were at risk for HIV or whether they were suspects of to be spies compared to just, you know, whether they were innocent job applicants. Okay, that had some effects on the probability of false positives and false negatives. And you remember, I'm not going to redraw the graph, but you might remember I drew a graph of that, and essentially it had type 1 and type 2 errors on each axis, okay, and there was a trade-off. Okay, so this trade-off is actually really a problem, and essentially that's one of the themes of this lecture. Okay, because you've probably heard the famous quotation by Lord Acton that power tends to corrupt and absolute power corrupts absolutely. Well, statistical power tends to yield false positives, and absolute statistical power yields absolute false positives. Okay, so you can never have your test as powerful as you want, okay? As usual, statistics there's no free lunch. Statistics is not a crystal ball, and you can sort of only do as well as you can with the data provided, okay? That's another theme of those lectures. Last time I said that Fisher information came out as that was the most information you could squeeze out of the data. Okay, so as I've already said, okay, a high likelihood ratio is evidence for H1. A low likelihood is evidence for H0. Somehow we have to draw the line, and then of course, as you asked, where do we draw it? Well, actually, let me give an example here. Okay, so you know, I don't want to whine about how I'm not used to using the board, especially after seeing such great lecturers. As I said, something that you get in physics. Okay, this is a problem about drawing these lines, okay? So in this particular example, these are my attempts at normal distributions. And so what are the effects of drawing the line going to be? Well, here's two normal distributions, okay? One of them has mean mu0. One of them has mean mu1, okay? Now, this is actually, in fact, a problem that comes up very frequently, okay? It's actually very frustrating for teaching because if you're actually trying to decide, if you're actually trying to decide if two normal distributions are actually different, okay, it's generally the case that you can't assume that you know what their variance is if you don't know their means, okay? So then it turns out you have to develop a new distribution called the t-distribution. You have to test against the t-distribution. Consequently, most elementary statistics books, they tell you lots of things about normals, and then suddenly from nowhere, they say, oh, use this table in the back of the book that has the t-distribution, and you do something called the t-test. Okay, that was a digression. Let me get back to my main theme here. Okay, so we have mu1 and mu0. We're associating H0 with this distribution, and we're associating H1 with this distribution. And so essentially what we have is, you see it depending on where we draw this line, okay? In this case, I am drawing it on the x-axis, so it's going to be closely related to k, but I'm going to write it as a c, okay? And if you look in the notes, there's a lot of extra details, okay? If you want to do homework, there are details that you need to do homework problems, because if you wanted to go back and forth between k and c here, you have to consult normal tables. But what I want to do is I just want to draw a picture, okay? So you're asking whether your actual data is in U0 or U1, okay? Well, what is alpha? Okay, well, alpha is reject H0 even though H0 is true. Okay, this is H0, okay? And you're going to reject it if your observation of the mean is greater than C. Okay, but this is a normal distribution. It spreads out a little bit. So this region here, okay, this region here is going to be alpha. Okay, and on the other hand, what's beta? Okay, well, beta is that you accept H0 even though H1 is true. Okay, well, that's going to be this region here. Okay, and there's sort of some very obvious things that come out of this picture. Okay, one thing is you're going to do better. You're going to be able to do much better if these actual means are further apart. Now, now the thing is that let's keep mu0 the same, okay? And so you could have mu1 that is very close to mu0, or you could have mu1 far away from mu0, okay? So the power is the probability that you're going to score H1 as being true if H1 is true. Okay, now let's see, where am I going to put C here? Okay, I'm going to put C here. Okay, well, basically, if this is C, then where the means are reasonably close, okay, this shaded region is the power pi, okay? If the means are further apart, okay, the power is going to be bigger. Okay, and please forgive my bad drawing, okay, but you can sort of see that, I mean, it's kind of obvious, okay, that it's easier to tell apart two distributions, especially two normal distributions, if their means are further apart. And then you could also talk about, and you can compute, full information is given in the notes. okay, you can compute what is called a power function. Okay, where basically what you're looking at is, okay, I've essentially made the point that the power in this case of comparing different means and asking are they different is essentially going to depend on how different mu1 is from mu2. Okay, and it tends to go up and flatten out. Okay, and now suppose they're right on top of each other. That's going to be alpha. Okay. Now, what you can show with the Neyman-Pearson lemma, and I can see that it's proved in the notes, okay? But there's an idea that's developed in the notes that, in fact, what Neyman and Pearson showed is that the likelihood ratio is uniformly the most powerful test. No matter what U1 is, okay? But in more general cases, things get a little bit more complicated, okay? Because what one is looking at more generally are composite hypotheses, okay, and that's where there's more than one distribution. Or that can in particular happen if you have to estimate some parameter in one or more of the distributions from data. So in that case, there's no uniformly most powerful test. And that can easily happen for these examples with normal distributions. For example, you could have a more complicated situation where H0, okay, so over here we had H0 was that mu equals mu0, and here we had H1 is that mu is greater than mu0. Okay, so in this case, it's a single-sided test because you're just looking at the same distribution and only in one direction. Okay, but the simplest example I know of a composite hypothesis, and this would be more likely to come up in reality, is that H0 is that mu equals mu0, and H1 is mu not equal to mu0. Okay? And so this immediately gives you a problem, okay? Because you could reject if mu1 is greater than mu0, Okay, that's the case I was considering over here. And that would be essentially saying if the sample mean was greater than C, and okay, you also have the possibility reject if X naught is greater than C, less than C, that reject if mu1 is less than mu0. Okay, so that would be if the sample mean were less than C. Okay, and essentially there you have two different things playing off against each other, because the power curve for this guy tends to look like that. So, for example, you don't know what the true mean is. Okay, you want to know if it's less than mu0, but it could be going in either direction. Okay, so you'd have to come up with some sort of compromise. Okay, for example, the absolute value of the difference. But in either case, it's not going to be the most uniformly, mu0 would be about here. It's not going to be the uniformly most powerful test. Okay, so this is actually a serious problem. Okay, it comes up a lot in these cases where you're considering many things happening at once. Okay, so there's many cells in this table. Here you're doing all of these tests simultaneously on the example of Galton's data. Okay, so what we do for the general case is very similar for what we do for the specific case. And I think since I'm going to be talking about composite hypotheses for the rest of this talk, I'm going to retreat back to here with the eraser. Okay, I'm going to leave this up because if you haven't seen alphas and betas before, sometimes sometimes it's good to be able to go back and refer to them. And I'm going to write the composite hypothesis likelihood ratio here because then, until I run out of space on the right, you'll be able to look back here, okay? And so what about a composite test? Okay, and so here we have a situation where in terms of, say, estimations, we want to test H0, which is some group of theta zeros. Okay, and you can see there's going to be, you're going to have to estimate lots of thetas in this example at once, okay? To H1, which is a group of theta 1s. Okay, now you could compare the maximum possible likelihood of all the theta zeros to the maximum likelihood of all the theta 1s. Okay, it turns out for reasons that I can't get into, what you actually want to do is you want to compare the maximum likelihood for theta naught to the maximum likelihood of theta 1 over all possible thetas. This can include thetas that don't occur over here. For example, it will be a maximum if you use a maximum likelihood estimator. Okay? And what we're going to do is we're going to let lambda be the ratio of the maximum of the theta zeros, the maximum likelihood here, over all possible thetas. Okay, so if H0 is best, if lambda is less than lambda sub c, and the probability that lambda is less than lambda sub c, given that H0 is true, okay, is going to be less than equal to alpha. Okay, this is the likelihood ratio test, and we typically work with the logarithm. Okay, and so if we're interested in log lambda, we're going to have a situation where the values can go from 0 to 1, and if the ratio is less than lambda sub c, we pick H1, and if it's greater, we pick H0. Okay, so there's lots and lots and lots of examples of these. Okay, this is something that, you know, if you need to know about it, okay, you can look up. And I'll just sort of mention, they're pretty much everything you find in standard statistics books and everything they teach you in standard statistic courses, okay? This Neyman-Pearson test is a special case, okay? Yes? You mean the log lambda? 1, 2, here? You're basically comparing the maximum likelihood of theta 0 to the absolute best likelihood you could get for all possible thetas for H1, okay? And the idea here is that you're often comparing a specific H0 to other, okay? Well, often H1 is essentially other, okay? So for example, okay, I'm glad that I drew this Galton case on the board, okay? H0 is that there's no selection for height among married couples, okay? H1 is there is selection for height Okay, but what's the selection for height? Okay, is it that tall men marry tall women? Or is it that tall men marry short women? Okay, either one is a violation of H0. Okay, you don't want to limit yourself to one or the other. Okay, and it's sort of like doing that two-sided test with normals. Okay, is mu1 different from mu0? Well, it could be different because it's smaller, different because it's, yes, okay. And, you know, as I sort of missed a couple talks as I went through my notes to sort of extract things, I basically sort of talking a lot, you know, I write slow, but I'm going to talk more this time because there's sort of a lot of, there's some really, really beautiful examples, but they require a lot of algebra to build up, and there's sort of no way we're going to get through them, especially since I see with shock that on this Friday afternoon I have already been talking for 50 minutes. Okay, so I'm going to pick up the pace here. You know, we have the next 2 days off. Oh yeah, I was going to say, this is used in all kinds of different cases, okay, that you can look up in books. It's used, the testing actually, if real things are, the two means are different, students t-test. Okay, I know from talking to some of you at meals, you're using things like ANOVA. Okay, this is what underlies ANOVA. You may be wondering, why haven't I talked about normal statistics, normal, quote, not normal distributions, but the kind of problems that come up frequently, such as significance of linear regressions. Okay, you use this for linear regressions, and variance comparisons, and chi-squared tests. Okay, so I want to talk about chi-squared tests, and I'm a little bit worried that I am not going to have enough time, but what I would like to do is, you've all heard at least of chi-squared. So I want to at least give you a specific, try to give you a specific example, okay? And you've got the textbook and you've got the notes. You may end up going back and looking at it. Okay, so the cleanest example, the cleanest way to get chi-squared is through a generalization of the binomial distribution called the multinomial distribution. Okay, and this is a generalization of the binomial distribution. You have mutually exclusive outcomes. Okay, binomial, you have two outcomes. Here you have k outcomes. And you have probabilities for each outcome. Theta 1, theta 2, theta k, okay? Of course, they all sum to 1. And then you have observations, okay? The observations are counts. X1, X2, XK, and all of the counts sum to n. In other words, you did n trials, okay? And there's k possibilities. There's all sorts of cases where this comes up, okay? Roulette wheel is one example, okay? Dice are another example, okay? There is a beautiful example in the notes that I urge you to look at, okay? There's a guy named Kurt Weldon. This is a famous case in the history of statistics, okay? And you guys are all graduate students. So luckily for you, you won't have your advisor do the following thing, which he had his students throw dice more than 12,000 times and write down what happened. and he put it in a big table. Okay, and there was a very famous argument at the dawn of statistics about how to interpret the table. The question was, were the dice fair or not? Okay, and you see, this is a very interesting point, because if you look at the table, okay, you may see one cell in the table. Okay, this is going to give you a contingency table like the Galton data. Okay, you may see one cell in the table that looks abnormally large. But how do you decide if the dice are fair? Okay, because you need to consider them all simultaneously. Okay, and it was essentially as a result of those discussions that a lot of these statistics were originally developed. Okay, so those are various examples. You do N trials with K outcomes each. Okay, now there's various properties of these things that you can read about in the notes. If you think about it, you'll see that multinomial trials will have a marginal distribution that's binomial. And the thing that makes them very interesting is, you remember things that Mukken was talking about this morning. Okay, he was talking about these big joint distributions. Okay, so that's sort of the key point. Multinomial is great for working these things out because it's actually a fairly complex joint distribution where the various variables are not independent. Okay, now how do you do a likelihood ratio test? Okay, well, essentially what you have is a situation where you've got your lambda. Okay. Oh, and so there's some other things here. Okay, so you can work out everything exactly. That's another reason they're very nice. Okay, because you can write the likelihood ratios down explicitly. They get a little ugly. But they turn out, and you might even see it just by looking, it's going to be n factorial over x1 factorial, x2 factorial, x3 factorial, xn factorial, theta to the x1, theta 1 to the x1, theta k to xk. Okay, so you have the likelihood explicitly. Okay, the MLEs are very simple. Okay, they look like the MLE for binomial. So theta hat sub I is simply the fraction x sub I over n. Okay, this is the sample fraction, and you can get this from using all the apparatus that I developed in the last talk. Okay, so now you can see that some little scraps of what you need to solve to do this problem are beginning to come out, okay? Because under the null hypothesis, you're basically going to be looking at the sample ratios, and then for testing, okay, what you've got is H1, H0 is that theta 1 equals A1, theta 2 equals A2, Okay. And now we come to this key point that I've been sort of making. H1 is otherwise. Okay, so we've set up this apparatus where we can test a whole bunch of things simultaneously. Okay, every cell in the table. Okay, so now we can easily write down the likelihood ratio test. Okay, the likelihood ratio test is this lambda that I so mysteriously alluded to up there, and logically asked me, well, how do you get that? Okay, well, it depends on the problem. Okay, but in this problem, I can write lambda down explicitly. Lambda is reject if lambda is less than lambda sub c. Okay, and now suppose that under H0 the expectation of x sub I under H0 is equal to m sub I, and furthermore, that's going to be n times a sub I. Okay, where the a sub I is it's going to be n times a sub I, where a sub I is the MLE estimator. Okay, so this is H0, theta 1 equals a sub I. And so now, essentially, we can write out lambda explicitly. Lambda is the likelihood of A1 AK under H0 divided by the likelihood of theta 1 to theta n under H1. And because we have all of this in explicit form, okay, we can actually write that as a product. A1 over theta 1 to the x1, the number of times we observed x1, all the way to, sorry, that needs a hat, all the way to AK over theta hat k. Essentially then, because m is n sub a, okay, that's going to be m1 over x1, big product, m sub k over xk. Okay, so the thing that you should note here is that if lambda is small, then minus log lambda is large. And so you reject if minus log lambda is greater than k. Okay, now I'm going to skip some steps. Okay, they're all there in the notes. Okay, but what we have this formula for lambda. Okay, and now what I want to do is approximate it. Okay, I want to approximate it by Taylor's theorem. And the thing that I want to approximate, taking into account the logs, okay, is that we're going to do a Taylor expansion of f of x equals x log x over m, okay? It's because of the minus log lambda that we've gone from m over x to x over m. Essentially what you can see in the class notes and also in the textbook, that the material comes in different order in both places, is essentially what happens is the leading term of the Taylor series disappears. Okay, and we're going to look at the first non-zero term of the Taylor series. Essentially, what that proves to be equal to is you essentially have that minus 2 log lambda is approximately equal to 1/2 times the sum of x sub I minus m sub I squared over m sub I. Okay? And this is also called chi-squared. And another way to look at this, okay, the mnemonic, okay, is this is observed minus expected. Okay, expected through the null hypothesis divided by expected. Okay, now this approximation is good if you have enough total observations. Okay, you don't have to do homework problems. Don't worry, for example, can you do it if every cell is bigger than 3 or bigger than 2 or whatever, okay? Look that up in the book, okay? Now, how, I called this chi-squared, but I haven't said anything about how it's distributed, okay? Now, if you start from this formula here, and you consider the case for k equals 2, okay, that's really binomial, okay, then you'll have x2 equals n minus x, a2 is 1 minus a, m2 equals n minus m. And you can essentially use this to substitute in, okay? And so for k equals 2, this turns out to come to x1 minus na over, how very interesting, a square root NA1, 1 minus A1, okay? Now, squared. Okay, now look, the reason I wanted to do this is I was frustrated for years, okay, as a user of statistics books before an unexpected turn in my life caused me to become a statistics teacher, okay, by the fact that the chi-squared distribution sort of appears by magic. You have a certain case, they just tell you to use it, okay? Well, look at the functional form of this. Okay, where did x1 come from? x1 came from adding up n trials. Okay, the expectation of x is n times a1. Okay, the variance of x is na times 1 minus a1. Okay, well, our friend, the central limit theorem, comes in. Okay, we're adding up these x's or random variables in the observations. Okay, so this x1 minus na over this funny square root, okay, na1 1 minus a1, okay. This is distributed like a normal random variable with mean 0 and variance 1. Is that a question? Oh, no, just a twitch. Okay, so this is said to be chi-squared. Okay, so that's distributed. This is distributed as a normal. Okay, but what actually comes up is the square of this quantity. Okay, so this is how we get the fact that chi-squared, okay, is distributed as the sum of a bunch of normals the square of normal random variables. Okay, and there's a notion that comes up with chi-squared distributions of degrees of freedom. Okay, in this case, there is 1 degree of freedom because the number of degrees of freedom is the number of normal random variables in the sum. Okay, so for the specific example I gave here, okay, this is k number of degrees of freedom equal to 1, okay? And you can look up the appearance of this distribution in textbooks. What happens is, for very low numbers of degrees of freedom, it actually is very, very concentrated on, it's only defined for positive values of x. For chi-squared, for 2 degrees of freedom, this is often a useful trick. It turns out it's exponential. But it has this characteristic skew appearance, okay, that looks something like this. This would be k equals 5. And as you increase the number of degrees of freedom, it gets more symmetric. And it moves to the right. And in fact, it's another application of the central limit theorem that essentially for large values of k, it starts to look quite normal. Okay, so there's some things I'm not going to talk about. Okay, just remember that it's a distribution for large samples. It's an approximation because your actual distribution in all these examples I've given you is discrete, but chi-squared is continuous. And in fact, they were originally put together for exactly these questions, like Galton's data, or figuring out if dice that can be that, have 6 possible outcomes are fair. Okay, now there's some other material that I hoped I'd be able to go through, but I can't, including I want to say about 5 words about p-values and confidence intervals before I get done. But I want to give you a little summary of what I'm not going to be able to cover explicitly because you might want to look at it in the notes. Okay, so what you have in the notes are a number of specific examples, okay, of the application of chi-squared to various kinds of contingency tables. Okay, this actually includes an application to evolution. Okay, and the application to evolution is something called the McDonald-Kreitman test. So one particular, I mentioned, for example, the multinomial distribution. That's a case where you're looking for a test for independence. You can use it on data like Galton had. You can also have something called a test for homogeneity, okay, where you're asking essentially for one of these tables if you constrain it so that the marginals are fixed, if you have the same ratios on each line. And so you might, since we are at a school about evolution, you should at least go look for the McDonald-Kreitman test example. And so what the McDonald-Kreitman test does, and actually I share a lab with Kreitman, I have to admit. I've learned a lot about it. In fact, most of what I've learned about population genetics I've learned from Marty. Because as you'll find out next week, I come very much from a developmental genetics background. But what's really great about the McDonald-Kreitman test is that H0 is that the variation in sequence that you see is neutral, okay, and H1 is that it's adaptive, okay, and this test has given rise to a big family of statistical tests that are used for all sorts of important problems in evolution. I'm not going to talk about them, but if you look in Nature News and Views or whatever is the equivalent of the science section of the New York Times in all of your respective countries, and it says something like, scientists find genes that evolve to change wolves into dogs, okay? How did they get that? Well, it's basically by sort of fancy applications of the McDonald-Kreitman test. Okay, I see that I need to design a new version of this course that fits into, actually cleanly fits into 3 lectures. I want to say a few words about the often abused p-values before I finish. Okay, and in case any of this is totally new to you, I am going to keep this board. I'm just going to skip over this board as I need more space, just so that you have a place to look in case you forget what alpha and beta are. Okay, I had problems forgetting them when I learned statistics. Okay.
Professor, just one little question.
Yes, Daniel.
What was this lambda sub L?
What was where I see lambdas? I don't. Lambdas.
Just in front of you, we have the composite test outcomes, Emil E, and then you define the likelihood ratio test,
right,
as the ratio of the maximum.
Okay, we're here.
Right, and now you say.
I deeply apologize. This is my utterly awful, hideous handwriting. Better? It's a lambda sub C. Okay, and the only sense that it's lambda sub C is this business that all through this whole introducing all of these concepts, we've had to draw the line somewhere. Okay, literally draw the line because we're working with probabilities. The likelihood ratio is continuous. All I mean is the critical lambda where we decide whether to accept or reject H0. Is that what you were asking? You thought it said lambda sub L, and you thought maybe that meant something. No, lambda sub C. Okay. Now we're getting to p-values. Okay, so it's bad. It's like 520. Okay, so I'm going to sort of make a speech about p-values. And then if you need more information, you know, as Mukun would say, go to the book. Okay? So look, the classical way to test is just what you said. Okay? You fix alpha at some level. Okay? And so a lot of times 0.05 is used. Okay? There's nothing sort of sacred about that. That's really sort of about the worst result you could have and not have people laugh at you. Okay, it's actually a pretty cruddy value of alpha, actually. Okay, and then you choose some test, okay, hopefully a high power test, keeping alpha fixed. Okay, that was this business. Absolute power leads absolute false positives. So when you do these tests, you always fix alpha first. Okay? And then you look for as much power as you can get, given that level of alpha. And then you look at the data and you accept or reject alpha. Okay, now, if you're not so constrained, and this is where we get to p-values, okay? The p-value is the smallest alpha, smallest level of alpha at which you reject H0. Okay, so a lot of times, you know, there's this convention, you should have a p-value of 0.05 or better. Okay, and you know, it's like it's 522. So you can go, you know, look at the notes. Okay, but the point I want to make about p-values is that they're grossly abused. They're really grossly abused because there is this tendency that when you learn this stuff at a superficial level, okay, you will treat a p-value of 0.05 as it's 95% probable that this result is correct. Okay, and if someone says that in a sort of naive, straightforward manner, I mean, look, I don't want to be rude, but they're trying to fool you, okay? Because there's all kinds of hazards you can get to. A lot of these hazards they're very endemic for things like that I know some of you are working on, you know, like looking at effects of polymorphisms in DNA sequences, okay? Because of course, if you do multiple tests, you know, you have a p-value of 0.05, that means that you're going to erroneously reject the null hypothesis 1 time out of 20. Well, if there's 100 tests, okay, well, 5 of them you certainly would expect, you know, would be erroneously, would be an error, okay? It doesn't mean 95% probability. A guy in my department who really changed my attitude about statistics, okay? I used to think statistics was boring but necessary. I mean, I confess to all of you. Okay, now I think statistics is really cool. Okay, it's a guy named Steve Stigler, and he has a great little speech he gives, the 7 pillars of wisdom of statistics, okay? And one of them is, don't torture the data until it confesses. Okay? And what does he mean by that? Okay, well, there is something that people do, and you have to be really careful about it. Like they think they want a result, and they sort of keep doing tests, and a lot of them don't work, and then they do one, oh, this is great. I have a p-value of 0.03. I'm going to write a paper and send out a press release. Okay, that's torturing the data until it confesses, because this theory is based on one single test. As soon as you do multiple tests, you're cheating. Okay? And similarly, since the alarm went off, I'm going to say about 3 or 4 sentences about confidence intervals, okay? Check the notes. It has very simple proofs of these assertions, okay? It turns out that the information in a p-value can be expressed in a very different way as a confidence interval, okay? And if you say that there's a confidence interval, it'll be between 2 points. Okay, and people sort of confuse this with like error bars. But the basic idea is not the same, okay? If you have a confidence interval of 95%, okay, that doesn't mean that you know the value of the estimator with 95% certainty, okay? It means that your confidence interval is placed randomly, but there's a 95% chance that it actually includes the true value, okay? And a very, very elementary proof, it's about, 8 lines, it's in the notes, it's something I do in class when I have more time. It's also in Rice's textbook, which you all have. Don't tell anyone where you got it. I was handed that PDF file by a student. I don't know where he got it. But I think Professor Rice has done very well from his textbook, because we're not taking bread out of his mouth. Anyway, they're exactly equivalent in their conceptual content to a p-value, okay? And actually, I've really told you just exactly enough about p-values to sort of hook you in to sort of the common parlance about this stuff. Okay, so, I look back on these 3 lectures. Okay, now, so for me, they were kind of a mixed bag, because I'm not sort of satisfied with the way that I compress things in. I asked Mukund after the morning lecture, oh yeah, he said he's been teaching that stuff for years. But, I think I got across a couple of key points. Okay, so the theme of these 3 lectures is every time we asked for less and less and less, but we got more and more and more. Okay, so the first lecture that I gave, okay, we tried to do it right. And I mean, really, Bayesian inference is really taking our full intuition about looking at experimental data and trying to express it in terms of probability. But because of issues with the prior and so forth, it's a little bit hard to get the quality of answers that you'd really want to get. So we gave that up. We gave up the posterior distribution. We decided that we would settle for point estimators at the maximum likelihood. Okay, but it turned out we weren't giving up that much. Okay, because Fisher's approximation theorem told us that those point estimators were normally distributed. It gave us their variance. And furthermore, the Kramer-Rao inequality told us that in some very basic sense, that was the best that we could do with the data. Okay? And then we gave up even more. Okay, we decided we were just going to make binary 0-1 decisions. Okay, and here we have, okay, I just sort of sketched it out for you. Okay, but I showed you that the chi-square distribution doesn't mystically come out of the table in the back of the book. Okay, and that it was developed for very interesting and tricky situations, okay, like this one, Okay, now this is a really old thing. It's not even from the previous century. It's from the century before that. I don't know the exact date. It's like 1880 or 1890. Okay, but this is very important for the kind of stuff that you're all working in, because you're working with tremendously complicated sets of data. We've got these sequence databases, et cetera, et cetera, et cetera. Okay, so these are the kinds of concepts that you need to use. Your research problems will be very diverse. Okay, so the point is, I'm not telling you how to do homework problems. Okay, what you should really be learning, you should be thinking about these basic principles, and you have some problem, think, oh yeah, Reinitz said something or other about that. And you go to the library and get the right book and read about it, because you're all really smart and you understand calculus. And then you can go solve the problem and publish papers and maybe be famous. So I'm giving my real lectures next week. But now it's 5:30 Friday afternoon, and I'm happy to take questions. But, then we can go take a nice break till Monday. And I think there's some planetarium thing we can go to, too. Right. Okay. Thank you very much. Yeah.
If you have, because, when you look at Stein's lemma tells you that the error probability should be exponentially small with n.
Right.
So if you have many data, you should have...
And if you have more data, you'll always do better.
Shouldn't you be more stringent when you have more data?
Yes. You should always be as stringent as possible.
Yeah.
I'm not being frivolous. I'm not trying to give a fully technical answer either, because it depends on the situation. You missed, some of the earlier lectures, but, no, I'm not saying that like, you missed some technical thing. I actually think I said in the first one, that I came to this stuff very late, because actually when I was a graduate student, it was all experimental developmental genetics. And what they told me there was, if you need statistics to interpret the results of your experiment, you should do a different experiment. And that's actually true. Yes, you should be stringent. And the best stringency of all is if you don't need a p-value. There's all this crazy stuff in medicine, of this so-called evidence-based medicine. But, of course you want evidence, but good evidence isn't testing against a null hypothesis. So I'll tell you guys, it happens that I'm diabetic and I take insulin. Okay, and you read all these papers about, some fancy drug, and there's p-values, and there's all this other garbage. But, when insulin was developed, there were no statistics used. Banting injected it into these comatose children that were about to die, and they woke up. So, no statistics required to interpret the results of the experiment. Of course, you don't, I'm not saying that what I told you isn't important, okay? Because the reality is you don't always have all the information you need, okay? For example, I mentioned McDonald-Kreitman test, and I'll leave you with an evolutionary thought, okay? I'll leave you with an evolutionary thought, okay? You're wondering if some mutations in the DNA are adaptive. Okay, why do you have to use statistics to find out? Okay, it's because of this horrible fact about real population genetics, that although it is absolutely clear that differences in fitness drive evolution over long periods of time, the fitness differences in actual real natural populations, as opposed to artificial populations people work with in the lab, they are so small as to be completely and totally invisible. So the only way you can get the information you need is through statistics. So, I sometimes make these kind of sarcastic sounding remarks, and I want to say that too. Yeah, if you can get it directly, but sometimes you've got to have statistics, and if you're going to do it, you got to do it right. Are there further questions, or shall we break for the weekend? Yes. Oh, yeah. Okay. One more. Well, one or more.
Yeah. Last day, when you told that when we do not know the a priori condition or do not know the distribution of the condition a priori, then we do maximize the likelihood function only.
When we don't know.
The theta distribution of this a priori.
Yeah, right.
Then the question was raised that how, because maximizing the likelihood function is dependent on the model. So how to compare between the models? So today you gave an idea how to compare between the models.
Yes.
Now my question is precisely like that. Suppose I have three models and I calculate according to your rules that pi 1, pi 2 and pi 3 for the three models. And pi 1 means the model 1 is the best according to this, the power of the test, and pi 3 is the worst. Now maximizing the likelihood, I get theta 1, theta 2 and theta d for the three model. I just want to know in that scenario whether theta 2 will be closer to theta 1 compared to theta t, means the same ratio will be maintained like pi or not.
Well, I would say that's really the reason why I said that in composite tests, you want to look at all the possible theta 1s, okay? So, you know, sort of the quick answer to your test is if you have this three-way situation, you should break it into binary tests, okay? The more complicated answer is, I bet, somewhere in the statistics literature that I haven't read, there's probably some theoretical analysis of what you do in that case, okay? But the reason you can take the first part of my answer is someone had fun with that, but that's actually not what people do. They do it by pairwise tests like that. And that's why you have all the theta 1s in the likelihood ratio test. Any more? Okay, next week you'll hear from me about fruit flies.